Okay, so last time we went over strong acids and bases and the definition of Bronsted-Lowry acids and bases, and this time we're going to talk about conjugate acid-base pairs, which we kind of did on the last one. We're just going to do it in a little bit more explicitly this time, and we're going to look at molecular level pictures of these reactions in aqueous solutions. So this has a lot of words on it, but it really can be simplified down thinking in terms of the hydrolysis of acid. The strong acid. There we go. Let's do that. So if I have HCl, there we go, and I react that with water, what do I get? A lot of it that way. Can you tell me about that back that way? I'm going to get, let's see, chlorine ion plus H3O plus aqueous liquid aqueous. Right, so what's gone on here? My HCl is becoming my Cl minus, so this is a proton donor. And that is our Bronsted-Lowry definition of an acid. Cl minus is now on this side. Let's see, it can accept a proton. So now it's a proton acceptor. That means it is the conjugate base of the HCl acid. So these two things are friends. Now, if my HCl is donating a proton, that means my water is accepting it, acceptor. That makes it a base. If it's a base, and it is tied in with my H3O plus, I can look at that and I know that's an acid. Well, it is the conjugate acid of water. And that's all this is defining for you. It's saying that if something is a proton donor on one side, then its conjugate pair is going to be a conjugate base on the other. So it'll be able to accept a proton to go back to whence it became. And the same with my base. If I'm accepting a proton on one side, on the other side, I'm going to be capable of giving up a proton. So now I'm an acid on the other side. So all this is saying we're plus or minus one proton. And we're going to start writing our acids and bases kind of like this, to where HA will define as an acid. It's just saying H paired with A could be whatever, anything. And then A minus will define as being a base, because you can look at that, can accept a proton, so that's my base. So let's practice our acid-base conjugates. Take a look at these and answer on a piece of paper, and then come back when you are done. And let's see what you come up with. All right, so I want the conjugate base of this. That means this is acting as an acid on my reactant side. If I'm acting as an acid on my reactant side, I'm giving up a proton, so I'm going to become NO2 minus. I want the conjugate acid of S2 minus. So S2 minus is acting as a base. It's accepting a hydrogen. And so let's just go ahead and say it goes to completion. So I'm accepting, so this is my base. And it's going to become a conjugate acid. So I'll have H2S. Cool. Conjugate base of HSO4, so that means I have it acting as an acid. If it's acting as an acid, then the conjugate base, it's giving up a proton, so SO4, 2 minus. The conjugate acid of HSO4. Okay, so if I want the conjugate acid, that means it's acting as a base on the reactant side. If it's acting as a base, then it's accepting proton, H2SO4. So I'm a base, I'm accepting on one side. On the other, I am now an acid capable of giving up the proton. I'm going to make a base, so that means I'm acting as an acid on the reactant side, so I'm giving up a proton that can now accept a proton and go back to what it was. So this one actually, which one of these? Probably more succinctly would be, instead of jumping ahead to 2 protons, would be something like HS minus. Probably more appropriate. All right, so let's take a look. What role is HCO3 playing in this reaction? Do you think it's acting as the acid, the base, or neither? Okay, so let's see. On this side of the reaction, I have 1 proton. On this side of the reaction, I have 2. So that means I am accepting a proton. I'm accepting. That makes me the base. The base. And that makes HF the acid. I look on this side, so fluorine ion is going to be the conjugate base. And H2CO3 is going to be the conjugate acid. Okay, so what is it in this reaction? Is it acid, base, both, neither, can't tell? What do you think? Okay, so let's see. HCO3, I have a hydrogen here and nothing here. So I am giving up a hydrogen, so I'm a proton donor. I am an acid on this side, and this is its conjugate base. On this side, I am going to definitely gain a proton, and OH is a strong base, so this is definitely a base becoming a conjugate acid on this side. Cool. So what does that tell us? Is HCO3 minus then an acid, a base, or both? What is that? Because we just define it as both. And in fact, there is a word for that. Amphoteric means something that can act as both an acid and a base. And amphiprotic, protic for proton, is something that can accept a proton or donate a proton. So according specifically to the Bronsted-Lowry acid-base definition is the amphiprotic. And if something can be both generally, then it is amphoteric. So for Bronsted-Lowry, those two terms are synonymous. They are the exact same with each other. All right, let's think about bonds. If I have a strong bond, which of the following is true? So I have a strong acid going into water. What does that say about the HA bond? Is it difficult to break, easily broken, releases a lot of energy, or a lot of energy is required to break it? So hopefully for this one, if we look at this, we're like, easily broken in water, right? Because it's easily broken in water because that's how we define a strong acid. We say that if I'm going to go HCl plus H2O, so hydrolysis of an acid, that our definition is that all of the HCl bonds are going to break. So what am I going to end up with? This chlorine ion aqueous plus my hydronium aqueous. So let's think about that. That means that this thing here, that bond is going to dissociate easily. Does that say that these bonds tend to be stronger? What do you think the Kc is? What did we say about the Kc for a strong acid? Didn't we say it would be pretty high? So if the equilibrium constant going one direction is really large, what does that tell us about the equilibrium constant going the other? It's going to be small, right? Because remember, if I flip a reaction, I go 1 over the equilibrium constant. So the reverse equilibrium constant is going to be really tiny. So what do you think that means about the bonds? Let's try that again with a base. So if my base gets stronger, so in other words, something that is going to give up or accept a proton easily. So as that gets stronger, what do you think is true about the bond it makes on the other side? So let's think about that. It's just like this. So my HCl bond is going to break really easily, and I'm going to form something that has a really small equilibrium constant. So what that tells me is that the bonds over here, this is much stronger than the bonds here. So these are going to be pretty weak bonds. And the same thing with my acid. And in fact, what we're going to see here is a little handy-dandy table that goes over the strengths of the bonds and how the acid-base conjugate reflects that bond. And I think the easier way to think about it is if something is super strong, we define that as dissociating completely, right? So if it dissociates completely, that bond can't be all that strong. And that means on the other side, it's going to form a very strong bond because I'm not going to get much of the wash coming back the opposite direction. And we can see that with our KCs. And so this handy-dandy table, and it's going to be posted with my notes, will really help to emphasize that for yourself. So it's just the complementary look then is if something is a stronger acid, it's going to have a weaker conjugate base, and a stronger base is going to have a weaker conjugate acid, and that really can be defined in terms of the bonds that they're making with each other. So, when you think in terms of chlorine ions, and I think chlorine and bromine for looking at our strong acids, if we say that it completely dissociates in water, and the beakers that we were drawing in are the images that we had in the last lecture, where I had like, here's my chlorine ion, here's a chlorine ion, here's a chlorine ion, and then everything else, I said then I'd have like 3 hydroniums, right? So this would be like Cl minus, Cl minus, Cl minus, and there's my 1 ion, and so I'd make like 3 of those. So if I completely dissociate going one way, then that means that even though I make a conjugate base, it's not going to be a very strong base. In fact, so little of it is going to do anything. We're really don't typically refer to those ions as being bases. And that's it for this. So I'll see you on the next.